Welcome to our first lecture on 5.2. 5.2 is a very challenging lesson, which is why we've split this particular lesson across 2 lectures. Now, before we begin 5.2, let me show you a little trick. At the very back of your textbook, if you flip to the back, you'll see on the left-hand side a whole bunch of formulas. You'll see that most of these are actually from Chapter 5. And this is really handy because when you need to do substitutions and switch back and forth between different identities, go straight to the back of the book. You see them all consolidated, everything from Chapter 5 consolidated on one page. Okay, so what we're going to be doing first of all in 5.2 is continuing where we left off in 5.1. 5.1, we worked on simplifying expressions. So we're going to continue with that. So this first problem is from page 208, number 22. And we're simply going to put this in its lowest possible version. Simplify. There you go. Okay, so it says, perform each indicated operation, which would be subtraction, and simplify the results so that there are no quotients, no fractions. So if I have 2 fractions and I'm subtracting them, then I need to have a common denominator, right? So what that means is I need to multiply the left and the right both by each other's denominator. So over here, this becomes sine alpha minus 1 over sine alpha minus 1. Remember, with expressions, you can only ever multiply by 1. This is just a form of 1. Over here on the left-hand side, I have sine alpha plus 1 over sine alpha plus 1. So now I have common denominator, and that common denominator is sine alpha plus 1 times sine alpha minus 1. So now we're going to combine that together. We have this negative sign right here. Here's the first numerator. Here's the second numerator. And then the new denominator, sine alpha plus 1 times sine alpha minus 1, is simply sine alpha squared minus 1, because this is the difference of squares. These are conjugate pairs, right? If you FOIL these, sine alpha plus 1, sine alpha minus 1, difference of squares, sine alpha squared minus 1. Now for our 2 numerators, this numerator right here is sine alpha plus 1. And these parentheses are not required. I put them here for effect. And over here, sine alpha minus 1. These parentheses right here are doing something, right? This negative has to distribute across these terms. So for my numerator, I'm going to have sine alpha minus sine alpha, right? So that's going to go away. 1 minus negative 1 is 2. And for my denominator, remember this, that one of our identities is that cosine squared plus sine squared is equal to 1. So what happens if we get sine squared alpha on one side, we move the cosine squared to the other side, and then this 1 we move to the left, I can rewrite this identity here in this form. These are algebraically equivalent, right? This is sort of off to the side thought process. So because these are algebraically equivalent, I can now replace sine squared alpha minus 1 with what sine squared alpha minus 1 is equal to, and that is negative cosine squared alpha. Now, 1 over cosine is the same as secant. So this then becomes negative 2 secant squared alpha. For our next problem, we are not simplifying, we are factoring. This is practice your trig factoring skills. We're going to use a method that is commonly used in calculus and other higher math. It's called U substitution. U is the letter U from the alphabet. So what we're going to do is we're going to notice that this is in a quadratic form, right? We have tangent squared, tangent first degree, constant. That is a quadratic form expression. So I want to replace tangent of beta with something really simple, like the letter U. I'm introducing U as a new variable, so I'm explaining what it's equal to. Let U equal tangent of beta. What does that imply? Well, then that implies that what this is equal to is 4u squared plus u minus 3. So if I need to factor, it's a lot easier to think about factoring in this form than in that form up there, right? So we need two factors of 12 that differ by 1. That would be 4 and 3. With 4 being positive and 3 being negative. And now that I've factored it in this form, I can now return back to the previous form by replacing u with tangent of beta. You are not required to use a substitution to help you factor, but for many students, having a substitution that brings a polynomial down to the level that they're familiar with is a really easy way to get through the problem. It helps them clarify their thought process, and this is something that is necessary higher in math to really simplify what you're looking at. But if you can go straight from the top to here, that's fine. You're completely welcome to skip the U substitution, but I would encourage you to still try U substitution because it's a valuable skill. Okay, so now we've got to the difficult part of 5.2, and that is we are going to begin to verify identities. This is the same thing as doing a proof, except that you do not have to justify your steps as you did in geometry, where you had to state the postulate or theorem. Instead, you just need to do a legal substitution and transform the equation on the left, or the expression on the left, so that it looks like the expression on the right. And the book introduces two different techniques, and one technique is to work completely from one side all the way until that one side looks like the other side. And so what they do is they start off by having the original problem, and then they rewrite the left or the right side of the equation, and then they do a series of steps until what's at the bottom is the other side of the equation. An alternative approach is to work both sides at the same time. Now, what I would recommend that you do is, since you don't necessarily know if you want to work completely from one side to the other, or if you want to work both sides at the same time, you can draw a line right under the equal sign. And basically transform the left-hand side as far as you can, transform the right-hand side as far as you can, and you can meet in the middle. It's kind of like working a maze, okay? When you're working a maze, you can either start at start and work all the way down to finish. You can start at finish and work all the way back up to start. Or you can start at start and start at finish and meet somewhere in the middle. Now, in a proof like this, where 1 is on the right-hand side, there's very little I would do to 1 to transform 1 to make it look like the left-hand side. 1 is already fully simplified. So instead what I want to do is I'm going to work exclusively on the left-hand side. But I am going to start every single one of my proofs with this red line, or a line, under the equal sign as a as a habit, just to show you that I will always do this, and then I will see which technique I need. All right, now, sorry, less talking, more doing. What I see here are some squares, and those squares should remind me of the Pythagorean identities. And so remember the trick, flip to the back of the book. If you flip to the back, you can just scan through those Pythagorean identities. They're under 5.1, fundamental identities. And I can see that one of them says 1 plus cotangent squared is equal to cosecant squared. And that would be the most natural substitution. So I replace 1 plus cotangent squared with cosecant squared. Now remember, the back of the book uses theta for the formula, or the identity. Here I have beta. So just make sure that what you write matches the variable at hand. So I'm going to rewrite this side, but I'm going to replace 1 plus cotangent squared with cosecant squared beta. Okay, so that's step 1. Step 2 is now to replace cosecant squared or sine squared with the reciprocal. You have to do it to one of them. You can't skip steps in a proof. So I'll go ahead and just replace cosecant squared with 1 over sine squared beta. And now I can see that when multiplying these two together, I do in fact arrive at 1. And so now I am finished. I have made the left-hand side equal to the right-hand side. Okay, next problem. Okay, here's number 54. This is on page 209. First, I'm going to draw a line under the equal sign. How do you choose whether to work on the left-hand side or on the right-hand side? Well, I'm drawn towards addition and subtraction, because often addition and subtraction require you to get common denominators, and whenever you're seeking common denominators, it gives you a way to transform an expression. So on the right-hand side, there is a fraction, right, because secant is 1 over cosine. So if you see fractions and you see addition and subtraction, you should be like moth to the flame, okay? So first, I want to start by rewriting secant as 1 over cosine. Now at this point, I can see, wow, I am subtracting two terms that do not have a common denominator. That means I need to get one. So to get one, we're going to multiply cosine, which is cosine over 1, right? I'm going to multiply cosine by cosine over cosine. I'm still only doing one step at a time. Even though I'm doing two transformations, they're happening to different parts of the expression, so I can do them simultaneously because I'm still showing all my steps. Okay, so now I have shown this multiplication, and you need to show every little step. A proof is a step-by-step explanation where you don't jump to conclusions. You really work through the process slowly. Now I have a common denominator, and so I can combine all this to be something over cosine theta. And that's 1 minus cosine squared. And even this might be considered jumping, because it could be argued that another intermediate step where we simplify this to cosine squared theta over cosine would be arguable to put in here, okay? Sorry if I'm being redundant. I think I just said argued and arguable in the same sentence. So anyway, let's continue here. 1 minus cosine squared theta. This should begin to look familiar. It is part of the Pythagorean identity that cosine squared plus sine squared is equal to 1. Therefore, 1 minus cosine squared is equal to sine squared. So I'm going to replace that numerator with sine squared. If in doubt, show more steps, not fewer steps. Okay, next problem. Suppose you're looking at this kind of problem and you think, I have no clue where to start. Well, when it comes to verifying identities, there is no substitution for experience. And this is why I've dragged this lesson over 2 lectures. When I taught high school, we would usually work on verifying identities for like a whole month. But you have that kind of luxury of space when you teach high school, especially because we did a whole year of trigonometry. So what I would say, if you're really struggling with identities, is to work through the examples in the book by covering up the whole explanation as to how to get through it, and try it on your own, and then just move the paper down 1 line at a time as needed for a hint to get you started again. Don't look through the whole answer first, because then it's going to look obvious and easy. Instead, cover up the answer to the example, try to work through it on your own, and only move that paper down a little bit at a time just to get the ball rolling again and to see how far you can get on your own again. And sometimes you're going to try things and you're going to end up going down a rabbit hole. And that's okay. You just get back on the horse and you start again. I think I'm mixing some metaphors there. So here, what I am drawn to is, I could factor the left and I can factor the right. In fact, in this problem, I'm going to illustrate for you how we can work on the left and the right-hand side simultaneously and hopefully meet in the middle. So on the left-hand side, I want to start with factorization. I can factor out a secant squared. And on the right-hand side, I can factor out a tangent squared. And all of those squares and ones make me think of Pythagorean identities. So I go back to the back of the book, and I look at the fundamental identities, and I say, oh, wow, look at that. Tangent squared plus 1 is equal to secant squared. Lovely. And so I replace tangent squared plus 1 with secant squared. Then I return to the back of the book again, and I look for one of the fundamental identities that involve secant squared. And since secant squared minus 1 would have to equal tangent squared, you can get that from rearranging that same identity we just used, I can replace secant squared minus 1 with tangent squared. And now the right-hand side and the left-hand side are equal because of the commutative property of multiplication. And you're done. Okay, so now we come to number 58. What I see here is a fraction that I really can't do much to. I can't think of anything I would do to that fraction to simplify it. I mean, there are creative things that you could try to do, but I don't know if that's even going to get me anywhere. On the left-hand side, right here on the left-hand side, I think, well, I could always square that binomial and see what happens. So let's do it. Let's square that binomial. This is where you do not want to fall into that very common algebra mistake. Remember that a plus b quantity squared is not equal to a squared plus b squared. When you square a binomial, you should always get a trinomial. So a minus b quantity squared is a squared minus 2ab plus b squared. And it's this form that I used right here, right? A minus b quantity squared, I have a squared minus 2ab plus b squared. So don't fall back to bad habits. Instead, make sure you are using strong algebra skills. Okay, so now I'm looking at this and I'm thinking, well, what can I do because that doesn't look anything like the right-hand side? Well, I do see some squares, so that's encouraging. I am completely winging this for you, by the way. I didn't practice this in advance, so you get to see me really just wing this. Okay, now, secant squared. I see a secant squared here, and the secant squared says that it's equal to tangent squared plus 1. Okay, I'll try that. Tangent squared plus 1. So I have just replaced secant of alpha with tangent squared plus 1, and now let me copy everything else. Oops, that's not a plus, that's multiplication. Now what am I going to do? Well, I can definitely collect like terms. So you try what seems like a reasonable substitution. You see that you can consolidate, collect like terms, and then you look at this and it's not even in quadratic form. There's nothing you can factor out, and you realize, I'm stuck. So what do you do when you're stuck? You realize that you've ran down a little bit of a rabbit hole, and that's normal and that's natural. And so then you just back up a bit and try a different juncture. So sometimes when you come to a fork in the road, you go left and you try it and it doesn't work. So you got to back up to the fork again and then try going right. Okay? So I tried this, which seemed like a reasonable approach. It didn't work. I didn't get anywhere. So now I'm going to back up a couple lines and try something else. It's important that you see that this is normal and natural in this process, okay? So another alternative substitution, because there are a good number of different possible substitutions you can try, is if the Pythagorean identity substitution doesn't work, then I would try going for fractions instead. So I'm going to rewrite secant squared as 1 over cosine squared, and I'm going to write each of these also as fractions. So that gives me minus 2, secant is 1 over cosine, and then tangent is sine over cosine, and then here I can replace tangent squared with sine squared over cosine squared, and this is where I realize I've hit gold. Why? Every single one of these denominators is a cosine squared alpha. Yes! Okay, what that means is I can combine this all into one fraction. And the denominator is going to be cosine squared alpha. And on top, what do we have? We have 1 minus 2 sine alpha plus sine squared alpha, which is in quadratic form. If I rearrange this, you can see that this is going to be equal to sine squared alpha minus 2 sine alpha plus 1. Now, what you can do is you can do an aside, okay? An aside is a note that you put off to the side where you do some work that's part of your proof, but maybe you don't want to bog down your proof, okay? So I'm going to go ahead and do that over here. I'm going to let u equal sine alpha, and I'm going to take this right here, and I'm going to say that sine squared alpha minus 2 sine alpha plus 1 is then equal to u squared minus 2u plus 1, which is equal to u minus 1 quantity squared, which must then equal sine alpha minus 1 quantity squared. Like that. Okay. So what I'm going to do now is I'm going to take this aside. I have included this as my work, but off to the side where it's still in logical order. It's still presented in a nice manner, but it allows me to bypass work, and I can now go straight from this line and replace that with this. Okay, so now my numerator is sine alpha minus 1 quantity squared over cosine squared alpha. Okay. Cosine squared alpha can be replaced with 1 minus sine squared alpha. I'm hesitating because I've got to the bottom of the board and I'm trying to figure out what to do. Okay, I do have a plan. I'm going to work backwards. I can actually see my ending in sight. So I'm going to get there by merging the left-hand side with the right-hand side. Now I've finally got here. This is the first point in the whole proof where I actually know where I'm going. The whole beginning is experimental, and once I get to a place where I can see how this becomes that, then I can tinker on the right or the left, however I want to do the presentation. So I'm going to go over to that side, and I'm going to multiply by the conjugate of the denominator. The conjugate of the denominator is 1 minus sine alpha. This is also a useful trick, multiplying by conjugates. Okay, so what that does is it turns my numerator into 1 minus sine alpha quantity squared, and it changes my denominator as a difference of squares into 1 minus sine squared alpha. And 1 minus sine squared alpha is equal to cosine squared alpha. Now let me point out something to you. 4 minus 7 squared is equal to 7 minus 4 squared. When you have subtraction inside of a square, you can actually reverse the order because the square is going to cancel out the order of subtraction flip. What that means is I can change the order of 1 minus sine alpha to sine alpha minus 1, and I will not change the value of the subtraction because of the square. Oh, yay, we're done. So that was the most challenging one of all. In the next video, I'll go through my open math.